and welcome back. So we continue. Let me share the file. Okay, so we continue with a compound pendulum. Of course, the purpose of this section is only to introduce you the center of percussion. For this purpose, we extract again the equation of motion for this compound pendulum. So from previous slide, you saw that the equation of motion for a system for a simple pendulum is L times by theta double dot plus G times by theta is equal to 0. Now we want to extract the governing equation for this compound pendulum and compare with the simple pendulum and extract the relation for this point A, which is called the center of percussion. So the equation of motion for this system can be easily obtained. J naught theta double dot plus omega d sine theta is equal to 0, which J naught is the mass moment of inertia about point O. And this is a nonlinear equation. As I told you, you can use the Taylor expansion for a small motion, for a small displacement. And you can consider when the theta is small, we can consider that sine theta is equal to theta. So instead of sine theta, we substitute theta similar to this simple pendulum, and we can extract the natural frequency for this system, which is equal to a square root of WD divided by J naught, and W is equal to M times by G times by D divided by J naught. This time you can see for a compound pendulum, the natural frequency is a function of the mass. So the mass will affect on your natural frequency. The D, which D is the distance between the mass center. Here you can see the distance between the mass center point G and point O, which is the fixed point of rotation. So the natural frequency is a function of this D. D is similar to the length in the simple pendulum, and J naught, which is the mass moment of inertia about, again, point O. So you can compare this equation with a simple equation, simple pendulum equation, and simple pendulum natural frequency, and we can find an equivalent simple pendulum for this compound pendulum. For this purpose, we calculate L, which is equivalent length for this compound pendulum, and it's equal to J naught divided by MD. You know that the natural frequency for a simple pendulum is a square root of G divided by L. Here, if you assume that in a compound pendulum, the length is equal to J naught divided by MD, you can use the same formula for the natural frequency of the simple pendulum to extract its natural frequency. But this time, this L is the equivalent length for your compound pendulum, and it will be obtained from this equation. So we can calculate this L, which J naught, as I told you, is equal to the mass moment of inertia, and it's equal to M times by K naught squared, and K naught is the radius of gyration about point O, about this point. You know these equations from dynamics. And K naught squared is equal to Kg squared plus D squared. Kg is the radius of gyration about point G, and D is the distance between point O and G. So you can substitute here, and if you continue your length, you can find another point A, which GA, or the length of GA, again is equal to kg squared divided by D, and point A is called the center of percussion. So in fact, we continue line OG to achieve to point A, which GA, or the length of the distance between point G and A, is equal to kg squared divided by d. And as I told you, kg is the radius of gyration about the mass center. Now we have one new point A. If you pin this compound pendulum instead of point O, you pin here at point A, and you release your pendulum, and it start to rotate and start to vibrate about point A, again the same natural frequency will be obtained. So this is the characteristic of the center of percussion. So we can conclude that no matter whether the body is pivoted from point O or point A, its natural frequency will be remain the same. As you can see here, this is the natural frequency. It's equal to GD divided by K naught squared, which is equal to G divided by L, and this is the equivalent L, or G divided by OA. So this point A is the center of percussion. And the application of this part or this section is, of course, we don't have the equipment in our lab, but sometimes you can find this point A using the experiments without any calculations. Okay, no questions so far, is it clear? Okay. The Rayleigh's energy method is an approximation method to extract the first natural frequency in your system. Most of the time we use the Rayleigh's method in continuous system. And here I just want to introduce this method. I mean, we don't want to use this method in our exam. And I just want to have a very short introduction to this method. And maybe in your assignment, you need to use this method to extract the lowest natural frequency in your system. So this is an approximation. The natural frequency which is obtained from this approximation method is usually less than the real natural frequency in your system. And to expand this method for a single degree of freedom system, we can consider the energy equation in two different points. For example, the first point, it will have some kinetic energy and some potential energy, as you can see. And we know that the summation of kinetic energy and potential energy in all the moments during the motion will remain a constant value. So in two different positions, the summation of kinetic energy and potential energy must be equal. So in a single degree of freedom system, we can assume that the kinetic energy and potential energy for the first point is when the U1 is equal to 0. It means that the potential energy at this position is 0. And the second point, when the kinetic energy is equal to 0. And which condition, for example, here, we can assume that this is a simple system which is moving, okay, mass M. This system is moving, for example, in X direction. The position 1, if we assume that this mass M will come till, for example, here, if we call it XM, which is the maximum X, we know that this mass will come to point XM and again back to its equilibrium position and again go to a negative value here, which is minus XM, and will move between minus XM and positive XM. So in this condition, in this system, the position 1 is considered when the potential energy is 0. I mean, here which is the equilibrium position, we know that U at this point is equal to 0 because the S-spring is in equilibrium position. So this is the position 1, yes. And the position 2, which the kinetic energy is 0, is considered here because at this time, the velocity of the mass is equal to 0 because the velocity at position X is equal to xm is 0. It will change the direction of the velocity, is moving to the positive direction. At xm, it will be stopped for a moment and change its direction and start to move to the negative direction of x. So at this moment, the kinetic energy is equal to 0, and this is the position 2. Of course, this position can be considered for position 2 as well, no different, because again at x is equal to minus xm, the velocity of the particle is 0. So you can write the T1 and U2 in two different position using your response. You know that the response xt is equal to a times by sine omega t. So the kinetic energy and potential energy using the xt or the response is equal to half times by m times by a omega cosine omega t, because the velocity of this particle is x dot, and x dot is equal to a omega cosine omega t, this term, and the potential energy is half k x squared, which x is a times by sine omega t. So the maximum value for the kinetic energy is occurred when cosine is equal to 1. You know that cosine and sine functions are between -1 and +1. I mean, the maximum value for cosine and sine function is 1. Of course, this is less or equal. So the maximum value for cosine and sine is equal to 1. So the maximum value for the kinetic energy and potential energy is equal to half m a omega a squared omega squared, and for u is half k a squared. So from this equation and using the energy methods, we can find the omega, which is again the natural frequency of your system. So we use the Rayleigh's. This method or this procedure is called a Rayleigh's method, and we use this method by writing the kinetic energy and potential energy in two different positions. And these two different positions, for example, here is considered. Here again, let me show you. Sorry. These two positions are this position 1 and position 2. At position 1, the potential energy is 0 and the kinetic energy is maximum. We know because the velocity is maximum. So at position 1 also we have the Tm or the maximum potential kinetic energy. And at position 2, the kinetic energy is 0 because the velocity is 0 and the potential energy at this point is maximum because x is maximum. Okay, so by using the Rayleigh's method in two different positions, we can conclude that the natural frequency can be obtained because the maximum potential energy and maximum kinetic energy must be equal. So half m a squared omega squared is equal to half k a squared, and here you can simplify and extract that omega is equal to a square root of k divided by m. So this is another method to obtain the natural frequency for a system, that we use one simple example for a ST-wave system to extract its natural frequency using the Rayleigh's method. Any questions so far? If you don't have any question, we can wrap up this session and we continue again tomorrow. Any question? Okay, so if you don't have any question, I will wrap up this session. Thank you for your attention and see you again on tomorrow. Thank you.